Hello, everyone. Welcome to today's presentation. I'm excited to talk about the fascinating world of computer memory and storage devices. The title of our session is Types of Memories in Computer System and Memory Storage Devices. Over the next few minutes, we'll explore the different types of memories, how they work, and their roles in computer systems. So, let's dive in and discover the essentials of computer memory together. Let's take a look at the contents of this presentation. We will start with an overview that includes the introduction, then move through the various types of memories, focusing on different categories like RAM, ROM, and cache memory. As we progress, we'll explore how these different types fit into the broader concept of memory hierarchy and classification. This structure will help us understand not only the individual components, but also how they work together to support computer performance and efficiency. So, let's dive into each section and see how they connect to give us a complete picture of computer memory systems. Welcome to today's discussion on memory in computing. When we talk about memory, we're referring to the physical devices that store both programs and data. These can be instructions that tell the computer what to do, or information that the program needs to function, like the current state of a game or a document. Memory can be temporary, like RAM, which is used while a program is running, or permanent, like a hard drive or SSD, where data is stored long-term. Think of memory as the computer's workspace, a chip that holds all the data and instructions you'll need later. Understanding how memory works is fundamental because it directly impacts the performance and efficiency of any computer system. Throughout this presentation, we'll explore the different types of memory, how they interact, and why they matter in the broader context of computing technology. Now, let's explore the different types of memories. When we talk about memories, we're referring to the ways our brain stores and retrieves information. Broadly speaking, there are several key categories. First, we have sensory memory, which is incredibly brief and captures information from our senses, like what we see or hear, just for a fraction of a second. Then there's short-term memory, which holds a small amount of information for a short period, usually around 15 to 30 seconds, enough to work with it temporarily. Moving on, long-term memory is where things get more interesting. This is where we store information over extended periods, days, years, even a lifetime. Long-term memory itself can be divided into explicit and implicit types. Explicit memory involves conscious recall, like remembering facts or events, while implicit memory influences our behavior without us even realizing it, like riding a bike or typing on a keyboard. Understanding these different types of memories helps us see how our brain manages the vast amount of information we encounter daily, and it also ties into the overall theme of how memory shapes our identity and learning processes. Let's talk about primary or main memory. This part of the computer is divided into two key sections. First, main memory is used to store data and instructions temporarily. Think of it as the workspace where the computer keeps things it's actively working on. It holds the data and instructions that are currently being executed, so the processor can access them quickly. An example of this is RAM, or random access memory. RAM is often called read-write memory because it allows data to be read from and written to it rapidly, making it essential for smooth performance. The second part is read-only memory, or ROM. Unlike RAM, ROM stores data permanently and is used mainly to store firmware or essential system instructions that don't need to change. Both of these types of memory are crucial for understanding how computers handle data and instructions efficiently during operation, which ties directly into our overall discussion of computer architecture and performance. Let's talk about random access memory, or RAM, which is a crucial part of any computer. A RAM chip is essentially an integrated circuit made up of millions of tiny components called transistors and capacitors. These tiny elements work together to store data temporarily so the computer can access it quickly. Now, the most common type of RAM you'll encounter is called dynamic random access memory, or DRAM. In DRAM, each memory cell combines one transistor and one capacitor. This combo is what allows the cell to store a single bit of data, either a 0 or a 1. Understanding how RAM works is key because it directly impacts how fast your computer can process information. Think of it as your computer's short-term memory, holding data that's actively being used or processed. Without sufficient RAM, your system can slow down significantly because it has to constantly fetch data from the much slower storage devices. So, in essence, RAM, especially DRAM, is the foundation for quick data access, enabling smooth operation and efficient performance. It's a perfect example of how tiny components come together to make our digital experiences seamless. Let's take a closer look at the different types of RAM, starting with static RAM or SRAM. SRAM is a type of semiconductor memory that uses flip-flops to store each bit of data. Because of this design, it doesn't need to be periodically refreshed like other types of RAM. This makes it quite fast and also means it consumes less power, which is a big advantage. However, the trade-off is that SRAM is more expensive and has a more complex structure, typically requiring 6 transistors per bit. Due to this complexity and cost, it's generally not used for high-capacity memory applications. Now, moving on to dynamic RAM, or DRAM. This type stores each bit of data in a tiny capacitor within an integrated circuit. The key point here is that capacitors tend to leak charge over time, so they need to be refreshed periodically to keep the data intact. This refresh process is an important characteristic of DRAM. Structurally, DRAM is simpler. It uses just one capacitor and one transistor per bit, making it possible to pack a lot more memory into a smaller space. That's why DRAM can achieve very high densities, making it ideal for applications where large amounts of memory are needed at a lower cost. Let's talk about read-only memory, or ROM for short. As the name suggests, ROM is a type of memory where new content cannot be added once it's written. It's essentially permanent. This makes ROM ideal for storing instructions that need to stay constant over time. These instructions are typically routine or basic functions that the hardware needs to operate smoothly. Because they don't change, ROM helps in controlling and supervising the hardware effectively. So, in the broader context of computer architecture, ROM provides a stable foundation of essential instructions that the system relies on. It's a critical component for ensuring consistent and reliable operation of the device. Now, let's take a closer look at PROM, or programmable read-only memory. Essentially, a PROM is a type of memory that you program once using a special device called a PROM programmer. This process involves writing the data onto the chip for the first and only time. One of the key things to remember about PROM is that once you've programmed it, the data is permanent. You can't change or erase it later, which makes it ideal for storing fixed data that doesn't need to be updated. This characteristic sets PROM apart from other types of memory that allow reprogramming or rewriting. So, in summary, PROM is a one-time programmable memory device, great for certain applications where data integrity over time is critical, but not suitable if you need to update the stored information later on. Today, I'll be talking about erasable programmable read-only memory, or EPROM for short. One of its key features is that the information stored on it can actually be erased, and then the chip can be reprogrammed to record new data. This makes EPROM quite versatile compared to traditional ROM, which is permanently written during manufacturing. To reprogram the chip, we use a PROM programmer, which essentially writes new data onto it after erasing the old information. Now, how does the erasing process work? It's done using ultraviolet radiations, or UV light. When the chip is exposed to UV rays, it clears the stored data, making it ready to be reprogrammed with new information. This process is what gives EPROM its reusability feature. There are different types of EPROMs, mainly the ultraviolet erasable programmable read-only memory, or UEPROM, and the electrically alterable programmable read-only memory, EAPROM. The main difference is in how they are erased and reprogrammed. UEPROMs use UV light for erasing, while EAPROMs can be erased electrically, which is more convenient in many applications. Overall, EPROMs are a significant step forward because they combine the permanence of ROM with the flexibility of reprogramming, making them useful in various scenarios where data needs to be updated periodically. Let's take a closer look at EEPROM, which stands for Electrically Erasable Programmable Read-Only Memory. One of its key functions is that its memory can be erased using electrical signals, making it quite versatile. This means you can update or modify the data stored there without having to replace the chip itself. In terms of utility, EEPROM provides an easy way to store both temporary and permanent information. Think of it as a kind of memory that you can program and reprogram as needed, which is especially useful for storing settings, calibration data, or other critical information that must be retained even when power is off. Overall, EEPROM is a flexible component that bridges the gap between volatile memory like RAM and more permanent storage, aligning perfectly with our theme of reliable, adaptable memory solutions in modern electronics. Now, let's talk about cache memory, which plays a crucial role in enhancing our computer's performance. Cache memory is faster and more expensive than RAM, but it's also much smaller, usually less than 512 KB. Its main function is to store frequently accessed data and program instructions so that the processor can retrieve them quickly without having to go all the way to the RAM every time. This quick access significantly speeds up the overall operation of the computer. There are two main types of cache memory to be aware of. The first is L1, or primary cache, which is built directly inside the microprocessor itself. Because it's so close to the processor cores, it provides the fastest access. The second type is L2, or secondary cache, which is located on the motherboard or very near the microprocessor. While a bit slower than L1, it still offers faster access than RAM and helps keep the processor running smoothly. Understanding cache memory helps us see how hardware design minimizes delays and boosts performance, which ties directly into the overall theme of optimizing computer efficiency and speed. Now let's talk about secondary memory. This type of memory actually complements the main memory, serving as a more permanent storage solution. Unlike RAM, which is temporary and volatile, secondary memory is designed to hold data even when the system is turned off. This is where we store programs, data that has been entered into the system, intermediate results during processing, and final results once everything is complete. Essentially, secondary memory acts as a long-term storage space, ensuring that our important information is preserved securely. Understanding this distinction is crucial because it highlights how computers manage not just immediate processing, but also the preservation of data over time. This overall theme of balancing speed and storage capacity is key in computer architecture, and secondary memory plays a vital role in that balance. Let's move on to slide 14, which is about classification. When we talk about classification, we're essentially discussing how we categorize or organize different types of data, objects, or concepts based on their characteristics. This process helps us make sense of complex information by grouping similar items together. In the context of our overall theme, classification is fundamental because it provides a structured way to analyze and interpret data more efficiently. Whether we're sorting types of diseases, categorizing customer preferences, or organizing machine learning models, classification helps us identify patterns and make informed decisions. Key points to remember are that classification involves defining criteria or features that distinguish different groups, and that choosing the right features is critical for accurate results. Also, the methods can range from simple rule-based systems to complex algorithms like decision trees or neural networks. So, in summary, classification is a powerful tool that underpins many of the techniques we use in data analysis and machine learning, enabling us to turn raw data into meaningful, organized information that drives better understanding and action. Let's talk about magnetic-based storage devices. First, when we look at preparation, these devices are typically formatted before use, ensuring the data can be written and read efficiently. Moving on to recording, data is stored on a disk in concentric circular bands called tracks. These tracks are like individual rings on the disk, which makes locating and accessing data faster and more organized. Now, some common examples of magnetic storage devices include magnetic tapes, which have been around for a long time and are great for backups, floppy disks, which were widely used in the past for small data transfers, and hard disks, which are the mainstay in most computers today for storing large amounts of data. Understanding these devices helps us appreciate their role in data storage history and their ongoing relevance in various applications. Now, let's talk about optical storage media. When it comes to capacity, these types of storage can hold a surprisingly large amount of data. In fact, some formats can store as much information as an entire hard disk. That's quite impressive, isn't it? Moving on to how they work, these disks are read by focusing a laser-generated beam of light directly onto the surface. This laser detects the data encoded on the disk, allowing for quick and accurate retrieval. As for examples, the most common ones you'll encounter are CD-ROM disks and DVD-ROM disks. These are widely used for storing music, movies, software, and more. Overall, optical storage media play an important role in how we access and share digital content efficiently. Now, let's take a look at memory hierarchy. This is all about how different types of computer memory are organized based on their access speeds, capacities, and costs. At the very top of the hierarchy, we have the devices with the fastest access times, like registers and cache memory. These are critical for quick data retrieval and processing, but they tend to be smaller in size and more expensive. Moving down the hierarchy, you'll find main memory, or RAM, which is slightly slower but offers larger capacity. Further down, there are secondary storage devices like hard drives and SSDs, which are much slower in terms of access speed, but provide significantly more storage at a lower cost. The key idea here is that this hierarchy balances speed, capacity, and cost, optimizing overall system performance. It's a fundamental concept because it helps us understand how computers manage data efficiently. So, while cache is fast but limited, secondary storage is slower but holds the bulk of our data. This layered approach is what makes modern computing both powerful and cost-effective. Thanks for following along.